Good morning. My name is Rob Skakun, and I am with the Canadian Forest Service out of Edmonton. And I've been working on wildfire mapping for probably about 10 years now. I'm a remote sensing analyst, so all my wildfire mapping is done with Landsat. And what I thought I would do was I thought I'd just compile some material of mapping wildfires, just really based on my experiences and doing this type of work. So what I thought I would do is break my presentation down into three components. Where first, what I want to do is just introduce the basics of fire mapping from Landsat. And this will be of interest to those that want to start using Landsat imagery or have seen Landsat-based fire maps before, and you're just curious in how they are created. And this part of my talk will probably take about 20 minutes. I'll pause after that, so if there's any questions, Karen will read them to me in the chat. Then after that, I'm going to just move on to talk about how mapping from Landsat can produce more accurate burned area estimates than conventional methods. And when I say conventional methods, I mean mapping by like GPS tracking or hand-drawn sketch maps. But this part of the talk will be around the National Burned Area Composite data set. And then moving on, the last part of my presentation will just be a short application study to show how can you use these more refined fire perimeters to calculate area estimates of caribou habitat. And again, after each of these components, I'll just pause for if there's any questions. So moving on. First thing I thought I would do is just set the context of what I mean by wildfire mapping. This is mapping based on when the fire is out. So the smoke has cleared, and what is left on the landscape is the burn scars. And what we want to do is map the perimeter of the fire to determine how much area burned. So again, this is not about mapping active fires and progression. This is mapping the burn scars to create a perimeter boundary, while at the same time not mapping the unburned features. And that can be unburned forest, which is also called fire refugia, but also removing the water from the perimeter map. And if you're curious about on these photos, they're from fires taken in the Northwest Territories, probably several years ago. But what I like about them is that you can really see the variability of a post-fire burn, with all the unburned forest patches, as well with the small water bodies in the burn scar. So what you see here are the type of burns that we're going to be mapping from Landsat. And since we're talking about Landsat, I just thought, I'll give a brief overview of the satellite. The imagery is at 30 meters pixel resolution, which in remote sensing, we call this a medium resolution sensor. There is 16-day coverage, which means the satellite passes over the same location on Earth every 16 days. However, and there is a however, there is overlap in the passes, and the overlap increases with latitude. So I think in areas of Canada, you can get around 40 to 60% overlap with each pass. So the cool thing about that is then you get more frequent coverage. The satellite captures spectral bands in the near and infrared portion of the electromagnetic spectrum, which is important for mapping wildfires, and we'll get into that part there. This is a United States owned and operated satellite, and many folks on the call probably already know the data is free to download from various websites. The site I use most often is Earth Explorer, but you could work with the data in the cloud through Google Earth Engine. I also just wanted to talk about the history of the Landsat mission, because I think it's interesting, there's been several satellites put in orbit since the first Landsat was launched back in 1972. The early satellites, 1, 2, and 3, they were actually a little bit more coarse in resolution. They were at 60 meters instead of today's 30. And they stayed in orbit for several years, but then ran the span of their life cycle and ended. But I want to jump to Landsat 5, as this has been the longest serving satellite to date. It was at 30 meters and had the near and shortwave infrared bands. And it's also referred to as TM, so that's an acronym for Thematic Mapper. My work would have started with Landsat 5. And although this chart shows it was decommissioned in 2013, it's interesting though, it actually stopped acquiring imagery in the fall of 2011. And I remember 2012 was a challenging year to map fires because we had no Landsat 5 imagery, and Landsat 8 wasn't launched until 2013. And all we had was the Landsat 7, which some of you may know, it has issues of its own with the scanline correction error. So that left streaks of no data across the imagery. And what we ended up doing was then gap filling Landsat 7 imagery with the overlapping passes. But what I want to let everybody know is that, like, for today, if you're going to map fires from Landsat, such as like the fires from 2021, it's best to use Landsat 8 imagery, which has the similar properties as Landsat 5, which just has more image bands to work with. And what's neat also is that this upcoming summer, we should have Landsat 9 imagery being collected as well. So that means more data collections from the Landsat series. And I also just want to briefly mention Sentinel-2 satellite, because this also has similar image properties to Landsat. I use Sentinel-2 data as well for fire mapping. It has a bit more of a finer pixel resolution and also has the near infrared bands that are similar to Landsat. There's actually some studies now that harmonize both of Landsat and Sentinel-2 to create image composites. And this is very good because you can create cloud-free imagery by compiling best available pixels into these composites. But Sentinel-2 is also very good because it has 2 satellites that orbit in tandem and they acquire imagery every 5 days. So compared to the 16-day window with Landsat, you get much more temporal coverage with Sentinel-2. It is a satellite owned by European Space Agency, and you can download this imagery for free as well, since it started being collected in 2015. So in this presentation, my examples are all based on Landsat, but I just want to point out you can do the same type of mapping with Sentinel-2. So that's just my brief overview of the satellites. And now I want to get into some kind of cool little pictures that we can look at to start wrapping our heads around what fires look like on the imagery. So this here is a 2021 fire in British Columbia, located near Kamloops. And we see those dark red pixels. And that is the burn scar surrounded by the healthy green looking vegetation. Now the burn appears as red because of the way I enhance the image in the RGB color display. But the enhancement also makes other areas appear as burned, which are in fact their dry, exposed grassland vegetation, which is what you see along that river valley. So just be careful when you're looking at imagery sometimes that, you know, a burned scar can also look like other features. But usually for most fires, especially those that burned more recently, you do get that really dark red tones on the image. And here's just another example, the White Rock Lake fire near Kelowna. And again, we see those darker red pixels, which are indicative of the burned scar. What you don't see on this image is all the smoke that was produced from these fires. And that would have made this image look like just a complete wall of whiteness. And be very difficult to use for image mapping. So the images I'm showing here and the one before, these were collected in the fall after the smoke had finally cleared out. So these are the ideal images that you want to use for mapping. In here, I also just want to show that for some areas where you have more frequent burn intervals, the older burn scars can still be present on the image for several years. The focus here is where we have the 2016 and 2018 fires, where parts of that area have now reburned in 2021. And in these burn over burn areas, the 2021 burn is a little bit more difficult to see because you've already lost a lot of the biomass from the previous burns. So in this example, the lighter pink pixels in the middle image are still part of that 2021 fire, and that part still needs to be mapped. And we'll go over how we're going to be doing all this mapping shortly. But what I also want to talk about is just the unburned patches that you see on a Landsat image. This here was an interesting area that I visited in 2015 with a colleague from the government of Northwest Territories. We were doing some field studies after the 2014 fire season. And when we were walking through the burned forest here next to the highway, in the distance, we saw this patch of green vegetation. So we walked to it and took a picture, as you see one of us standing there. And it was literally an island of unburned vegetation surrounded by the very severe burned forest. Now, I don't understand why this area never burned, but it certainly confirmed to me that the small green patches that we see on an image are indeed non-burned forest, or again, this fire refugia that it's also called. Now, the size of this patch of forest was probably a few hectares. Now, in my opinion, the smallest unburned island that can be reliably mapped on Landsat is 2 hectares, and that's equivalent to 9 30-meter pixels. Now, you can go as small as 1 hectare, but the smaller you go, the more uncertainty there is in your mapping, excuse me, or your non-mapping of these unburned forest patches inside the burned scar. I also just want to show here that I thought, this was interesting, that when you look at an image, not every red pixel you see in the, in the middle of the green forest is a fire. So here's an example of a blowdown event from this past summer that occurred in Northwest Territories, just south of Trout Lake. And by just looking at this area in the image, it could be interpreted as a fire, but as we see from the photograph, this is in fact fallen trees from the severe downburst. And a really good way to, determine whether or not this is fire or not is just to use the satellite fire hotspots and overlay them. And if there's no satellite hotspots, then there's a good indication that this is not a burn. Next thing I want to show you is this graph, because this will help you understand how fires are mapped on an image. The green line is an example of a spectral response curve for healthy green vegetation, where we have percent reflection on the y-axis and the continuous wavelengths of the electromagnetic spectrum on the x-axis. The red line is a spectral response curve for a burned forest. Now, for that green curve, we see very high reflectance on the near infrared because healthy green vegetation is very reflective in this part of the spectrum. And moving down the curve, it is less reflective in the shortwave infrared because of light absorption from the moisture in the leaves. Now, the spectral response of burned forest is the opposite. And as we see in this graph, the greatest differences are in the near infrared and shortwave infrared. It's not in the visible part of the spectrum. So this is why we'll be utilizing those near and shortwave infrared bands for mapping fires. Now, it's also important to note that every fire will have a different looking curve, and that's dependent on several factors, such as the severity of the burn, the type of vegetation that burned, pre-fire conditions, such as whether the ground was moist or it was a burn over burn event. But the key thing here is, as long as you have these differences in the spectral response between the healthy pre-fire conditions and the burn post-fire, you will be able to map the fire. So next, what I want to do is do a step-by-step example to map a fire. So we'll kind of just go through it, slide by slide on how we're going to be mapping fires from Landsat. So here's a full Landsat scene that I found from last summer. It is smoke-free and it's certainly cloud-free, which is huge bonus when you see an image like this. But you can also see that there's a lot of burned scars. So in order to know which of these burned scars are from 2021, what we do is that we overlay our fire hotspots from 2021. So for this, I'm using the MODIS hotspots, but you can also use hotspots from other satellites such as VIIRS. Now, with the hotspot data, you get an acquisition date for each point. So this is very important to look at to ensure you are mapping the burn after the fire is out. Okay, and that would be the last acquisition of a hotspot. Now, this image we can see is from late September. My previous slide, I think, showed it was September 30th. So And that's generally the end of the fire season. So with that and the hotspot dates, I'm very confident we can map fires on this image because those fires have been extinguished. But the area I'm going to focus on for doing the mapping is just down in this bottom corner here. So here we have this corner zoomed in. And again, we know that this area burned from 2021 because of our hotspots. But I've also downloaded a pre-fire image that has the healthy green vegetation. Now, just some points to know about the pre-fire image. What ideally you want to do is acquire an image from 1 year prior to the burn. You can go back 2 or 3 years, but it's always better to be closer like to that post-burn image. And you also want to be collecting or selecting that image around the same time period. And that's just to reduce then any differences in the imagery in the spectral response due to vegetation phenology, because we are going to be getting into some image differencing as we move along here. The next thing we want to do in this mapping procedure is create exclusion masks. And really this means removing areas from the image that could mistakenly be mapped as fire, or it's just areas that we want to include in our statistical analysis of the burn pixels. So some of the common exclusion masks are for water, and this can be done using an existing water layer or a mask feature, such as from Canvic. But you can also classify the image into a water class. But in this example, I'm using a water layer that was available in Google Earth Engine. It was from the Hansen Global Forest Change product, so I just created the water mask out of that. But other features that you may want to exclude are clouds and cloud shadows. And luckily, you know, there are none on this image, but if there are, then there are tools that you can use to create these masks. Now, one thing too with clouds, like if there are thin clouds or haze, you can sometimes still see the burn scar, especially through the infrared channels because they are longer wavelengths. But still, you know, ideally try avoid any cloud or haze on the imagery if you're going to be doing mapping. The last exclusion mask you want to consider is an agriculture mask. And really that's just for if you're mapping fires in the parkland or on the boreal fringe, and you don't want the agriculture fields to be included in the mapped area, then create a mask for those fields. And Agriculture Canada has a land cover map that they produce. I believe it's annually. So that's a good data layer to use for a mask. The next thing that I do is that I use the hotspots to create fire processing units. And I like to think of these as spatial units in which to process each fire event for mapping. I create 1,500 meter buffers around the hotspots, and then I dissolve the overlapping buffers into a single polygon. I mean, this becomes then the processing unit for the fire. So the idea here is then that within each of these spatial units, so each of these fires where we have this envelope that we created, we can then extract the unique spectral signature of that fire, because again, remember, all the fires are going to have those different curves based on, you know, the time of year it burned, what burned, those sort of things. Now, for image mapping, it's most common to use what is called the normalized burn ratio. And this is simply a ratio of the near infrared and the shortwave infrared. But depending on which Landsat satellite you're using, the near infrared would be band 4, if you're using Landsat 5 and 7, and band 5, or if it was Landsat 8. For the shortwave, it's band 7 for all the satellites. And we also compute the normalized burn ratio for both our pre and post fire images. Now the output of the normalized burn ratio, or MBR, I'll say, it looks like this on a post-fire image, which we call T2, and then our pre-fire image that we call T1. But you'll notice on the T2, the burned pixels are the ones that are the darkest in color. The lighter grays are the healthy green vegetation, and the pure white that you can kind of see in there, well, remember, those are the areas that I had masked out as water. So we know that none of those water bodies are going to be mistakenly mapped for fire. So that essentially just is no data. And at this point in our steps, we're about halfway there to map in our fire, because the next thing what we want to do is that we want to create what's called the differenced normalized burn ratio. And this is simply just subtracting our pre and post fire NBR images. Now, there are some variations to this equation. In our next guest speaker, we'll probably talk about them, but for the purposes of mapping the burned pixels, the simple equation seen here works well. The offset at the end there, usually that's just a constant value to correct for differences from the vegetation phenology. But from using this equation, you can now see that the lighter colored pixels are now have become the burned area. So now at this stage, we're set up to do our image mapping. Now, if we extract all the pixels within a fire processing unit that I'm pointing to there on the screen, we can create a histogram of the differenced NBR values. So the next step here is now to threshold, which means to set a range of differenced NBR values to classify as burned pixels. So in this example, the highest peak is healthy vegetation, and that also includes some of the unburned patches. But it's that smaller peak to the right, which is our burned pixels. And remember, we've already masked out water, so there's no water pixels in the sample, it's only forest cover. And typically, anything greater than 0 is burned. But I don't like to use 0 as the beginning of your threshold, because you can then sometimes capture some of those unburned pixels. So for this example, I set it to 0.2. And that's the lowest point in this bimodal distribution. But one can get even more complex than just the manually thresholding, by looking at a histogram. And you can start getting into some automated stats analysis to set the range of threshold. But once we do, set that threshold, basically what we're doing is that we're classifying the area within the processing unit so that all burned pixels greater than 0.2, those become the mapped area. And that's what you get in the top right of my slide here. But it looks messy. So a lot of times that mess we call noise in the classification, and these are single pixels that get misclassified. And it can be caused by a number of things, but a lot of times it's just anomalies in the image. But what we do though is that we run filters to clean up the noise until we get a more accurate looking burned area. Then we run a conversion tool to transform that raster output to a vector polygon, which we then overlay on the post-fire image to determine the quality of that mapped product. Now, overall, that right there, the steps I went through, that is a very basic and also an accurate way to map fires on a Landsat image. I just want to show this example here, because this is another fire to look at that's just a little bit more up close, but you can see the quality of that Landsat delineation around the burned scar. And notice that the unburned patches and water are not mapped. And that perimeter, it follows a very close delineation around the burn, even over that previous burn there on the right. Now, I also just want to say, that there's some fires that are actually, pretty challenging to map. So after you go through this process of image mapping and then create the fire polygon, you may need to manually correct parts of that fire perimeter in the GIS. And that's just simply because with the image processing, the thresholding, the filters, and so on, they're not always perfect. And you're going to need that human interpretation element just to come in and then just make some adjustments to that final product in the GIS. So some of these more challenging areas where you may need to do that are in the burn over burns, insect infestations like spruce budworm or mountain pine beetle, just because the red attack trees can sometimes look like fire. And if you're mapping a fire in those stands, it can get a little bit challenging to where the extent of that burn scar is. Wetlands, rocky outcrops, and clear cuts are other examples where it's really good to do a quality check in the GIS afterwards, just to make sure that your fire polygon is as accurate as it can be. Now, this is just my last slide on this first part of my talk. And I just thought it was interesting because I just wanted to show how fast regeneration can occur within the same growing season of a fire. So in this example, which is located in southern Manitoba, a fire burned through most of May. But on May 30th, we have this really good image of the burn scar. But if we were to use a July or August image to map the fire, look how much green up has occurred since May. So it'd be really challenging to accurately map that perimeter with summer imagery. And that's why you want to use a post-fire image that's as close as possible to when the fire was extinguished. And again, use those hotspots to really help you determine when that fire is out. So that's the first part of my talk. Karen?
Hi, Rob. I have one question here from Emily. She would like to know, is this a fairly standard approach to mapping burns? Do other countries or provinces follow the same steps?
Yes, it's very common. The difference normalized burn ratio is probably one of the most popular indices that remote sensors use. But there are different ways to use that equation. There can be relative difference normalized burn ratio. So the answer is yes, but it just comes in different forms. And I just did the simple subtraction of the pre and the post. But yeah, this is the most common way that fires are being mapped with Landsat. The more simple way to do it sometimes is some people will actually just take an image and you can just manually draw a perimeter on the image as well. But then you're getting into really labor intensive work. So it's much easier to do the image differencing and then do the fresh thresholding and then convert to polygon after that. Another question, Karen?
You had two other questions, but both of those you answered throughout your presentation. So that's all for now. Thank you.
Okay, so I'll move on.
That would be great.
Okay, next thing I want to talk about is the National Burned Area Composite. And I'll be referring to it as NBAC. And it's a fire polygon data set that I produce each year with a small team. Now, in NBAC, we build a national map by piecing together multiple sources of fire data from various sources. The dark red areas on the on this graphic that you see here, these are fires that are mapped by Natural Resources Canada using Landsat and Sentinel-2. The peach colored areas that you see, these are from the fire management agencies, and they use a variety of mapping methods such as GPS delineation from fixed wing or helicopter. They also use satellite data with Landsat and Sentinel-2, and they may follow the exact same procedures that I had shown in my previous slides. And they also use some very high resolution data, which comes from the air photos. Now, the reasons why we map fires when we already have fire data from our agencies, which is compiled into the Canadian National Fire Database, is because the quality of the fire data in our national database can vary. And so to help explain that, here are two reasons why we want to map fires from Landsat. The first is that the aerial GPS polygon approach can overestimate burned area simply because of its broad delineation around the burned scar, and also just by not removing water and unburned forest patches within that burned perimeter. The second reason why we want to map fires with Landsat and NBAC is that not all fires are mapped, or some are partly mapped by the agencies. So in this example here, you are seeing actual fire data that is in the Canadian National Fire Database based on the 1989 fire season. But just to expand a little bit more on these two reasons that I just gave on the previous slide, on my first point, there are different mapping methods used by the agencies, and I tend to generalize them as being high quality, which is really good delineations of the burn. But there's also lower quality, which may be the end product of the satellite hotspot buffering, a sketch map, or the combination of a burn maps over a cross-border fire where one agency, did a really good job mapping that fire, but then the agency on the other side didn't capture all of it. So the key thing here, though, is that in NBAC, we want to include that higher quality agency perimeters because they're already super good. But it's for these lower quality perimeters where we incorporate the satellite data to improve the fire mapping. So here are these lower quality fire polygons again on the right, which we remapped using Landsat. And remapped using Landsat based on those procedures that I had shown in the first part of my presentation. So the idea now is that these Landsat fire polygons would be included in NBAC because really we've improved the burned area by the more precise boundary, and we've also removed those unburned forest patches and the water from the perimeter interior. And I just want to show now another example of that second point I made about missing data. We see recent burn scars from this 1998 image when we overlay the hotspots, which would have come from the AVHRR satellite. We can see that the burn scars are indeed from 1998. And now when we overlay the CNFDB data, we see that some of the fires were mapped, but not all of them. So in NBAC, what we want to do is take that image that you see here and we map it. And now we've captured the full area that had burned. And in doing so, we've now mapped close to 28,000 hectares that was not previously captured by the agencies. Now, overall, when we compare the area burned from NBAC and the polygon version of the Canadian National Fire Database, we found that there's 8% less total burned area since 1986. And that annual area burn has decreased by about 200,000 hectares per year with NBAC. The years with the largest amounts of burned area had the largest reductions. So for example, in 1989, the NBAC mapped about 6.6 million hectares, while the Canadian National Fire Database reported 8 million hectares, which is a difference of 1.4 million hectares, which is quite significant. And again, the purpose here is to show you that the finer delineations of fires produced using Landsat that do not account for the unburned forest patches or water within that perimeter estimate, they provide a more accurate estimate of burned area. And this is just my last slide on the NBAC before I move on. We did publish a paper in 2020 on the NBAC product. And it provides a lot more details on how the data set is produced. And I just want to let people know that we are working on a follow-up paper to NBAC where we explain in more details how we extended our time series back to 1986. And it's also going to include the application example of the undisturbed caribou habitat, which I'll be showing next. But for those that are interested in using the NBAC data that has these Landsat fire perimeters, it is available free to download on the Canadian Wildland Fire Information System. So thanks for that, Karen. Are there any questions on the National Burned Area Composite?
None have come in yet.
Okay.
So feel free to go ahead.
Okay.
Thank you.
So for the last part of my presentation, I just want to show an example study using NBAC that I recently did in collaboration with the government of Northwest Territories. And it was to determine if an improved burned area data set derived from Landsat would change the amount of undisturbed habitat for caribou protection in the NT1 range. So for this study, we are comparing wildfire data sets from the NBAC and the Canadian National Fire Database. So for some background first, the National Recovery Strategy by Environment Canada sets a target of maintaining at least 65% of the NT1 range in an undisturbed condition to allow the caribou population to be self-sustaining. Now, undisturbed habitat includes areas in the range that have not been affected by wildfire in the last 40 years and not within 500 meters of an anthropogenic feature. Now, the NBAC dataset extends 34 years. So for this analysis in scenario 1, we combine the NBAC with this Canadian National Fire Database to create a 40-year wildfire disturbance layer. And in scenario 2, we used only the Canadian National Fire Database polygons. And both wildfire data sets were combined with the anthropogenic disturbance layer produced by Environment Canada, which in the NT1 range is mostly seismic lines and roads. And then we dissolved it into a single disturbance layer. And in our results, we found that NBAC led to a 1.6 million hectare increase in the amount of undisturbed habitat for the NT1 range. Now, in comparison to the 65% threshold, using the Canadian National Fire Database data, which Environment Canada uses, we found the proportion of undisturbed habitat was above the level at 68%. But with NBAC, it was 71%, and that's just based on the addition of those 1.6 million hectares of undisturbed area. And just going back to this example, which I had shown earlier, but this time now I've overlaid the agency polygon, which is shown in light blue. We can see again why the Landsat delineation reduced the amount of area burned. And that's because of that finer delineation around the burned scar and not mapping those unburned forest patches in water. And yes, the water was included in the amount of undisturbed habitat in this analysis because that is what the National Recovery Strategy does as well in the calculations. Now, this is just my last slide on this. The government of Northwest Territories partitions the NT1 range into smaller planning regions. And we can see that this increase in the amount of undisturbed habitat occurs in every region except one. So the one region we had a decrease is in the Yukon. And we determined the reason for that is because we had mapped fires in NBAC that were missing in the Canadian National Fire Database. So therefore, the amount of burned area increased. But what is interesting, I find, is that in the Southern Northwest Territories region, which I think has the most fire activity of all the subregions, we saw the largest increase in undisturbed habitat for caribou at just over 700,000 hectares. And again, this work was done in collaboration with the government of the Northwest Territories, And all the numbers and values have been reviewed by the Department of Wildlife. So this was just, again, the purpose of this was to do an application study just to see how refined estimates from Landsat can help improve our knowledge of undisturbed habitat in the context of the caribou. So that is my presentation for today. I believe that was my 45-minute time slot. So I am free now for any questions that you may have.
Thank you, Rob. I do have a question here from Peter. He says, it appears you are mapping canopy scorch. If no canopy is scorched from wildfires, is this classified as not burned?
Yeah, it's a good question. That really depends on the timing of the imagery. If it's a grassland, you got that grassland area within the forest stands. If that got burned and you were able to get an image really close after that fire, you will capture it because that scorched grass will still be there, but grassland regenerates really fast. Like it greens up probably within a month, depending on where you are, but I've seen it green up very quickly. And by that point, if you're acquiring an image a month or two after, you may miss that as burned area. And then, yes, it would become an unburned forest patch. So for the most part, yeah, it's the scorched trees. It's that loss in the crown biomass that is being captured.
Okay, so I was just going to build on Peter's question. I think he may be alluding to a lower intensity or a surface fire. So that would answer whether or not a surface fire that doesn't necessarily have total crown consumption would be captured.
Yeah, again, I really think it's really based on the timing of your imagery. You can capture those fires if you can get an image that was acquired right after that fire. But the spectral signature of those burns on the non-forest area, those grasslands, yeah, they can show healthy fairly quickly afterwards.
Okay, a question just came in from Tanya Letcher. She would like to know, what is the approximate CFB required to be recorded?
Approximate
CFB.
I'm not sure what
crown fraction burned. Crown fraction burned.
Oh, that I don't know. I understand what you're saying. What proportion of the crown has to be burned to be detected? That is something I don't know. It's a good question though.
Perhaps this is one our teams can look into and try to address on March 4th if there is indeed an answer. And right now I don't have any other questions. We'll kind of give it maybe 15 seconds here and see if anything else comes in. Well, with that, Rob, I think what we can do is maybe use this as an opportunity to take a little bit of a bio break before Ellen starts at 10:30. So thank you very much for your presentation. That was great, very informative. If everyone could meet back here just prior to 10:30, we will leave this video open and admit the new people entering. And we'll queue up Ellen to start shortly. Thanks, everybody.